All right, I'm going to move this. But what you want to get out now, if you haven't already done so, is, oh man, go ahead and get out your PowerPoint notes or Google Slides notes, whatever you want to call it. You won't need it yet. Yes.
I did not think that.
You don't have this packet? Did I even turn this on? There we go. Let me see if I have any more. Huh. Bear with me here real quick. Let me go see. I'm going to pause this. I'm going to pause this video here right quick. All right. Yeah, I'm pretty sure I'm still recording on this. I hope. Okay. Let me get a drink of water here real quick. Okay. So, we are going to be looking at energy transformations and efficiency in today's discussion. Okay? We've been talking about work, power, machines. But when we are talking about those concepts, we really need to remember a couple things. We need to remember the conservation of energy, as well as look at the efficiency of machines. And so, going back to the first concept, conservation of energy, what we need to remember is that energy will readily change from one form to another. And energy is simply changing. It's not being created. It's not being destroyed. It simply takes on another form. Okay? And that the total amount of energy that started the whole process will be the same after whatever process has taken place. So if we think about a roller coaster ride, anytime I have an opportunity to incorporate roller coasters into my discussions, I'm going to take it. Okay? So here it talks about conveyor belts, but it's not conveyor belts. It's a chain lift for most of them. Okay? It's a chain lift. Now, that chain lift is going to take the roller coaster on the majority of roller coasters, not all. It's going to take it to the top of the hill, and every inch, every centimeter that roller coaster climbs to the top of that first hill, it is gaining energy. It's actually gaining gravitational potential energy because it's getting higher and higher from the ground. So it gets to the top of that hill and begins to descend on the downhill side of that first hill. As that roller coaster is descending, its energy is transforming. It's going to kinetic from potential. Because it started as potential when it was high up. As it starts to move, kinetic energy is the energy of motion. So the roller coaster is moving. Therefore, its kinetic energy is going to increase. Now, what you can't see over here because of this box here, it's not a 100% return on investment. Okay? Nothing in this world is, which is when we start talking about efficiency. Okay? As the roller coaster is going on throughout its entire run, it's constantly transforming its energy, gravitational to kinetic, back and forth, back and forth. But because we live in a real world, small amounts of that energy, as it's being transformed from gravitational to kinetic, is going to be not lost, but transformed into other types, like heat, sound, vibration. Okay? That's because we have friction in our life. Friction is the concept that likes to take away energy when it can. So, I can't do that. Okay. So as we are doing this whole transforming of potential to kinetic and vice versa, we're going down that hill. I believe this is a picture of King Ka in New Jersey. Yeah, I'm kind of obsessed with roller coasters. What's that? So as the object is descending, the potential energy is going to decrease and the kinetic energy is going to increase. The balance or the transforming of potential and kinetic is very similar to that of a teeter-totter or seesaw, whatever you want to call it. As one goes up, the other goes down. And it constantly does this throughout the ride. But even though we are having this constant transformation and these little bits and pieces of energy transformed into other types, like we said, with heat and sound and vibration, the total amount is always going to be the same. Because even though we have smaller amounts of kinetic potential as the ride goes on, that those little bits of energy that are released as sound, heat, and vibrations, if we were to put those back into the whole equation, well, we'd have the same amount of energy present. So again, like we've already said, most of the potential or most of the energy of the roller coaster is potential at the top of a hill. At the bottom of the hill, it'll be mostly, if not all, kinetic energy. And then in between those 2 points, they are transforming. And this concept of kinetic and potential energy transforming throughout the duration of a roller coaster is going to be a concept that we are going to hopefully recall towards the end of December, or the semester, I want to say, because we have a plan to hopefully do something fun, like I mentioned. Okay, it does have something to do with those 2 words. Nothing crazily fancy. Okay, but it's a fun but engaging activity that we spend a good amount of days on throughout a week. So, but it all goes back to this. This one?
Yeah.
Air as vibrations, is that what we needed? Okay. So, moving on as we continue our trek down the track of the roller coaster. So as kinetic energy is transformed, typically we will see the kinetic energy of the object decrease and potential energy start to increase again. Because as we go on that first hill, oftentimes we will go back up another hill once we reach the bottom of that first hill. And so once we reach that bottom of that first hill and start going up another hill, we start to slow down. The amount of kinetic energy begins to decrease while being transformed, that bless you, into potential energy, because we are going back up a hill. So our height in comparison to the ground is going to increase. Therefore, our potential energy is going to increase. So we've seen it for the 3rd slide in a row, basically. As one goes up, the other goes down. Constantly doing this transformation throughout the entire process. Now, as you're kind of writing this content down, kind of give you a little tidbit of information of roller coaster design. If you've ever been on a roller coaster, raise your hand if you've been on a roller coaster before. So everybody in here, excellent. So you go on that big tall hill a lot of times, and then you drop down. Is there really any other hill in that whole run it's going to be as tall as that first hill? Typically, no. And that's because we have friction. If we did not have friction, we would be able to go back up the same size hill over and over again. But why can't we? Besides saying friction, because we have friction, why can't we come back up a second hill that is the same height as that first hill? Was that? Okay, gravity's going to work against us. Okay, that could be a component. What else? What's preventing us? Well, it goes back to the last few slides. Okay, as we are constantly doing this flip-flopping back and forth between kinetic and potential, the friction is causing heat. It's causing sound. It's causing vibrations, which are forms of energy that are being taken away from that roller coaster system. So some bits of energy are getting kind of removed and taken to another place. So that's removing any kinetic energy that it had at the start of going down that hill. So it doesn't add up to it being able to go up to the same height. We're going to talk about an example here in just a second when we talk about bouncing a tennis ball. Okay? It's kind of the same concept. Unless the roller coaster itself has mechanisms, either a second lift hill or other means, like it's called a linear induction motor, basically electromagnets. Unless it has that somewhere down the line, it's never going to have the same height as the original hill, as long as it's a lift hill. Has anybody been to Busch Gardens, Tampa Bay? Fewer and fewer people are. Well, they have a roller coaster there called Cheetah Hunt, and it has 3 separate launches throughout the entire ride. And the second one launches you straight up into this big top hat type situation. If it didn't have that, there'd be that second launch, and there's no way it could get back up to that height. So they had to input additional energy because so much energy was lost in the travel prior to that, it would not be able to make it up there. So there are ways to making roller coasters a way that you want them to, but you have to obey physics. All right? And so I mentioned the tennis ball. What happens when we have transformations of mechanical energy? Yet another term that we've discussed before. When energy is transformed, not all of its kinetic energy is going to change into elastic potential energy or vice versa. And when we say elastic potential energy, we're just talking about potential energy in general, okay? And it can be transformed into other non-mechanical forms. When an object moves, kinetic energy is going to compress the air around it, causing sound. It also is transferred as heat energy, like I've been saying for the last 10 minutes or so. But again, it's not disappearing. It's not going bye-bye. It's not being destroyed. It's simply changed. Simply changed. Think of a bouncing tennis ball. Okay? This image on the right kind of sums it up really nicely. If you just drop a tennis ball, don't put any additional energy into it. You just let it bounce. Each subsequent bounce will be shorter and shorter than the one previous to it. Because as that ball is dropping, it's encountering air resistance. As that ball impacts the ground, it loses some of the energy to heat and sound waves. So we don't get 100% return in that. And so it can only bounce up so high on its next bounce. And that process continues until eventually that ball is no longer bouncing. Because we are losing little pockets of energy due to sound and heat. Think about a basketball. Does anybody play basketball here? Okay. So imagine if physics didn't apply. And all you had to do when you wanted to dribble a basketball, you just push it down one time, you could walk down the court, not even touch the ball in terms of having it bounce back to you at the same height every time. Kind of weird, wouldn't it? But instead, what do we have to do when you dribble the ball? You have to push it down every time. You are continually adding energy to that ball so that it's going to make up for any of its lost energy from the motion of it bouncing. Every time you hear that ball hit the ground, that sound you hear, that's energy that is being removed from that system of the ball bouncing. So that's why you're constantly using your hand to dribble. So hop forward about 4 slides. Hop forward about 4 slides. We're on to efficiency. Okay? We talked about power, we've talked about work, we've talked about machines, and now we've talked about the transformation of energy. How can we minimize energy loss from a machine when it's doing its job? And how do we measure? Okay? Unfortunately, not 100% or only a portion of the energy put into a machine is actually going to do useful work. And we call it useful work what the machine was intended to do. It's all because we live in a real world. We have friction. Machines can also do incidental work that does not serve any intended purpose. You know, a lot of the things we've been hearing about in terms of efficiency are automobiles. You know, we have in most of our cars are internal combustion engines. Okay, and that involves fuel. Fuel has chemical potential energy within the bonds of molecules in gasoline. We add a spark to it, that starts a chemical reaction. When we have a combustion, or when we do that process, we hear it, don't we? We can hear those little miniature explosions in the engine. And since we're dealing with explosions, it heats up. And what's left is, you know, we put into the mechanical engine where we turn other parts of the motor. And they in turn turn other parts of the motor. Okay? So the whole idea behind making an efficient vehicle is to minimize or be able to retain and reuse some of that lost energy, like the heat. Wintertime, a lot of our heat, where does it come from? That we blow into the car. A lot of it comes from the engine. See, we're trying to reuse some of that stuff so we can benefit us. But again, the more things you have down the line, the more energy you're going to lose because of friction. Again, that's another reason why you have to make sure every moving part in an engine or anything that's going to move outside of the engine is well maintained, well lubricated to help minimize friction. Using a pulley to lift a sail on a sailboat, okay? If it's an old rusty pulley, it's not going to be very good, okay? That's why you want to take care of it. Now, we can calculate efficiency somewhat easy, and I want you to add this little bit to this formula. So what this says is efficiency is equal to useful work, so again, the work that is intended to do, divided by the overall work input. How much work was put into trying to do this task? And then multiply it by 100%, because most of the time efficiency is reported as percentage. Okay? And again, no machine is ever 100% efficient. We simply try to get as close as we can to that number. Once you've finished writing that down, I want you to get your calculator out. If you don't have a calculator, just sit tight, but I would like your assistance. I currently had to remove the battery out of my calculator because it no longer worked, and I'm having a hard time finding a new one for it. So, We're going to do a practice question before I give you your homework on efficiency. Are we ready? We have a sailor who's going to use a rope as well as an old squeaky pulley to raise a sail that weighs 140 newtons. He finds that he must do 180 joules of work on the rope to raise the sail by 1 meter. Excuse me. What is the efficiency of the pulley, and express your answer as a percentage? So first we have to figure out what is what. What is useful and what is our input work? Okay? What is our work that we're getting out of the machine compared to what is the work we're putting in? Okay? So again, efficiency is equal to useful work divided by input work times 100%. So I'm just going to call it UW and IW for useful and input. Let's look at the problem. Let's try to identify which is which. Let's look at input work, IW. Okay, right here, second one. Anybody take a guess as to what our number would be when we're trying to pinpoint input work?
140.
You say 140? Okay. 50-50 chance here. Anybody want to take a shot of what the other one might be?
180.
180. Here's why. He finds that he must do. So he has to put in 180 joules of work. Okay? So that leaves us with, Matthew, our useful work of 140. But hold on! What unit is that 140 in? Now, is that the appropriate unit for work? What must it be? Joules. So we got to pause for a second. It's not that difficult. To calculate work, it's force times distance. So the force is 140. And how high did he have to lift it? 1 meter. Excellent. So, really, he's going to put it in the tray. Thank you, Josh.
Heck yeah. See you guys.
So, in actuality, how much work did we get in return? How much useful work was done? 140 joules. Okay. Now, you got to pay attention to that because it may not always be, a distance of 1 meter. Okay. So 140 joules. So now we can go ahead and put this in there. So efficiency is equal to 140 joules divided by input work as 180 joules times 100. Go ahead and calculate that. Nolan, what'd you get? What was it? 0.8? 77.8%. It's not a terrible percentage in terms of efficiency. Could be worse, but it could also be better. What might be a way that we can better this efficiency or raise this percentage?
Use a better pulley.
Use a better pulley or properly maintain this pulley. Could be old, it doesn't matter. But if it's squeaky, that means there's going to be friction. Try to reduce that friction, and you may not have to put as much work into raising. All right. So those are the types of problems that you're going to see today. Now I'm going to pause. I'm going to actually finish this